Welcome to the introduction video of my thesis. Let's first start at the beginning. At CERN, near Geneva, we are operating the largest particle accelerator ever built by humankind. This is the Large Hadron Collider. Inside this 27-kilometer long machine, beams of particles are accelerated to near the speed of light. The beams are made to collide inside huge detectors, where we attempt to measure exactly what happens at microscopic scale. There are 4 major detector experiments at the LHC, of which the Alice detector is relevant for this thesis. The Alice detector is optimized to measure collisions between heavy nuclei, meaning that it can handle collisions that each produce thousands of particles. Why are we interested in heavy ion collisions? Let's have a look. In this simulation, we see the protons and neutrons of 2 heavy nuclei collide with one another. The collision converts all the excess energy into many additional particles. But something more happens. The temperature of the overlap region gets so large that a phase transition occurs, which transforms the hadronic matter into a soup of deconfined quarks and gluons. This is what we refer to as the quark-gluon plasma, which was also the state of matter that was filling the universe only microseconds after the Big Bang. We are only able to recreate these droplets of Big Bang matter in these violent collisions. In this thesis, the physics of both small and large collision systems is studied in great detail by using the photon as the main object. The photon has its own unique role in studying the quark-gluon plasma, as the mean free path of the photon in a strongly coupled medium is much larger than the size of the system that is created in heavy ion collisions. This means that once a photon is created by or in the QGP, it is able to escape the medium unaffected, and as such carries valuable information on the space-time dynamics of the QGP. However, these photons are hard to distinguish from the background as there is an abundance of neutral meson decays which have large branching ratios into multiple photons. It is thus needed to measure the properties of these mesons with high precision. This thesis presents measurements on neutral meson production and direct photon correlations from small to large collision systems at the LHC. The main results of the thesis are the invariant yield of the π0 and eta meson as function of their transverse momentum measured in pp, p-lead and lead-lead collisions. The nuclear modification of cold and hot nuclear matter for the π0 and eta meson. A detailed model study that reveals why the combinatorial background of photon pairs is not well described using conventional event mixing techniques, including a way to improve it. In another model study, it is shown that selecting pp collisions based on their shape is unable to significantly enhance the amount of jets contained within that sample, which is contrary to current literature. One of the important highlights of the thesis is the first measurement of direct photon elliptic flow in lead-lead collisions at the LHC. The thesis also presents a first look at direct photon HBT at the LHC, as well as a chapter listing ideas for promising future measurements.